Last time we talked about velocity. Today the topic is acceleration. Acceleration is simply the rate at which an object changes its velocity. Therefore, its definition is a change in velocity divided by a change in time, which brings us to our next major formula. Again, notice the arrows. The arrows simply indicate direction, that acceleration, like velocity, is a vector, and that at times you'll have to pay attention to the direction. And over here, we have the change in velocity and the change in time. Time does not really have a direction. It's not a vector, so that's why it does not have a little arrow above it. There are lots of different types of acceleration. When you simply hear the word acceleration, you probably think about speeding up, because that's the common use of the word. Technically, slowing down is also an acceleration. It would just tend to have a negative number instead of a positive number usually. Often we call that deceleration. And when something changes its direction, instead of going east, it starts to turn to the north or turn to the south, then it's experiencing a type of acceleration called centripetal acceleration. For centripetal acceleration, there's an entirely different formula. Now let's talk about the units of acceleration. Since acceleration is a velocity over a time, its units should have velocity units on top over time units. Velocity units are meters per second, and time units are second, and so the standard unit is meters per second per second. Unfortunately, meters per second is kind of an ugly unit with a fraction on top of a fraction. So what's commonly done is that meters per second squared, which is equivalent, meters per second is the same thing as dividing by time twice. So meters per second squared is used instead. Like velocity, there are other units that are often used. Typically, the English system uses feet per second squared instead of meters per second squared. And quite commonly, you'll talk about accelerations in terms of g's. 1 g is the typical acceleration that an object experiences here on Earth due to gravity. And so it's quite common to compare accelerations to that of gravity. Here you can see a note card of specific values that you could use. Of all the stuff on this note card, you can probably get by memorizing just this fact, that 1 gravity, 1 g on Earth, is equivalent to 9.8 meters per second squared, which is also equivalent to 32 feet per second squared. Typically, we work in the metric system, and so the 9.8 number is going to become very familiar to you by the end of this unit. Let's look at a couple specific problems involving acceleration. Suppose you're driving, and all of a sudden, a raccoon or deer or whatever animal walks onto the road in front of your car. You would slam onto your brakes, and suppose you decelerate at a rate of 28 feet per second, or 28 feet per second squared. If you had been traveling at 100 feet per second, how much time would that take for you to stop? Now, before we go too far, 100 feet per second, that seems pretty fast. How fast is that in miles per hour or meters per second? Let's use the approximation tool that 1 meter per second is approximately 2 miles per hour, which is approximately 3 feet per second. So 100 feet per second, if I divide that by 3, that's roughly 30 meters per second. And if I multiply that by 2, that means I'm going roughly 60 miles per hour. Pretty fast, especially on a road where there might be raccoons. Anyway, if I'm traveling at 100 feet per second and all of a sudden I start slowing down at 28 feet per second, we can approximate the time it's going to take for us to stop. After 1 second, we've gone down from 100 to 72 feet per second. After 2 seconds, we've gone down from that to 44 feet per second. After a third second, now we're down to 16 feet per second. So somewhere between 3 and 4 seconds is how long it's going to take to stop. Now we can calculate this directly if we use the formula. Acceleration is a change in velocity over a change in time. Our acceleration is 28 feet per second squared, and our change in velocity is 100. We had been going 100, and now we're going nothing. The amount of time it takes is delta t, and we can flip-flop these two. Delta t is equal to 100 divided by 28, so 100 divided by 28 is 3.5 seconds, 3.57. So here's another example. It's quite common to measure car power by its ability to accelerate from 0 to 60. For instance, this particular car can go from 0 to 60 in 4.8 seconds. Is that good? What is the average acceleration? And how does that compare to gravity? These are some questions we'll calculate. Let's start by just naively plugging in some numbers into the formula and see what happens. Recall that acceleration is the change in velocity over change in time, which would be 60 miles per hour and 4.8 seconds, which equals 12.5. But 12.5 what? 12.5 meters per second squared, 12.5 miles per hour squared, 12.5 G's? Hardly. 60 miles per hour, and on the bottom here, 4.8 seconds, means that our units here are 12.5 miles per hour second. If you're confused, it's rightly so. Miles per hour second isn't really a standard unit. The problem is we're kind of mixing units. 60 miles per hour and 4.8 seconds don't mix well together. Now, we know that 60 miles per hour is exactly 88 feet per second squared. So let's use that instead. Now if we use the average acceleration as change in velocity over change in time and use 88 and 4.8, this calculates to 18.3, and the units would be feet per second on top per second or feet per second squared. Now this is something we can directly compare to gravity. You remember that gravity is 32 feet per second squared. That's what 1 G is equivalent to. And so if we divide the two of these, 18.3 over 32, that corresponds to 0.57, or let's say 0.6 G's. Not bad. Now I'm sure some of you are wondering if there's any cars that accelerate with higher than that as G's. If we look down here, the reliable source of Wikipedia tells us and shows us that there are many cars that have accelerations even faster than the one that I have listed. Appears the car with the greatest acceleration currently is the Ariel Atom V8. Of course, that doesn't look like a real car. Anyway. Now, while this car has great acceleration, 0 to 60 in 4.8 is pretty good, it's not as good as gravity. So my follow-up and final question is, how fast will our car accelerate from 0 to 60 if we simply throw it off a cliff? To answer this, we'll use one final time the formula. A is change in velocity over change in time. And this time we know the acceleration is 32. That's the acceleration of anything thrown off a cliff. And we know the velocity is 60 miles per hour, which is the same thing as 88 feet per second. And we want to know how much time that would take. So we've seen this trick before. Let's flip-flop delta t and 32. And we'll calculate 88 over 32 and get 2.75 seconds. So unless you start telling me that your car can accelerate from 0 to 60 in less than 2.75, you're not as good as I can do just by driving my Ford Taurus off of a cliff.